So I'm going to talk about the graph-based metrics for for evaluation of point cloud simulations coming from virtual test environments. Today, we had many conversations and talks that they were mostly on RGB camera, but we will have a switch of gear here, and we will be more focused on point cloud simulations. So in short, if I want to explain how the whole pipeline works for us, normally we have some LiDAR point clouds. We have our RGB camera. We do some fusion. We have our ground truth ready to go. At the same time, from this fusion of data, we can make our digital twin. Normally, we use some softwares like Carla, and then from this, we make our simulated LiDAR scans. So one question that come up is how good is these simulated scans? Sometimes we might think that this is not good enough, but in reality it's actually good for what for the purpose of our work, and sometimes we are correct. This is actually not good. So just to give you an idea, when we talk about the qualification steps for VTE, we have 3 steps. One of them is about the input data itself, that normally we want to do some audit to make sure that this input data is good. Remember that maybe many people in machine learning believes that garbage in, garbage out, that would be the same thing for VTs as well. Then we want to make sure that we do a good documentation and we know how to use these VTEs. And finally, when we make the simulations, we want to check that this simulation is geometrically valuable and valid. And one thing that matters is, like, depending on the reason that we do this test, we might have different criteria. So going to our VT pipeline very quickly, we do data collection using different sensors like LiDAR, IMU, GNSS, and RGB. And from there, right away, we can have our real LiDAR scans. From this data, we do both SLAM and odometry to do point cloud regeneration, and we will be able to find the trajectory of the vehicles that going forward inside the real environment. From these, we can reconstruct point clouds, make a mesh, and then send this mesh inside our simulator like Carla. And for the example of this work, we use 128 channel setup within Carla, and that was the LiDAR we were using. And we do some ray tracing, and we make our simulated LiDAR points. Again, the idea is that we would like to have a metric comparison between this real LiDAR and simulated LiDAR scans. We are doing lots of data collections, and we do lots of in-house work, end-to-end products, all the data collection to making these digital twins happen inside our labs in London, Ontario. So, of course, we are part of the government, so the capital is Ottawa, so we go to Ottawa a lot, and there we have a test track. So this work was actually done in collaboration with Transport Canada, where they helped us to work in a real test track and do a tester. For this work, as I mentioned before, we use a 128-channel LiDAR. We have done the same thing for a 32-channel LiDAR as well. So here is the point cloud reconstruction for different routes that we have taken. They have kind of funny names that they call these routes, for example, Bravo. The difference between these routes is some of them are having lots of curves, some of them are paved, some of them have very harsh surface, some of them have lots of vegetations around them, some of them we have some fake small buildings, so different scenarios to simulate. So from this regeneration, we do a map generation. Again, nothing too special about this part. Again, a very important thing is that our final product is as good as the mesh that we produce. So if the mesh is too if the mesh is not too good, then your final result won't be good as well. That being said, having a good mesh and doing mesh generation is still one of the very challenging things in research. So here you can see one example of this simulated thing. This is not actual simulation. This is our real LiDAR scans moving around our own campus in London, Ontario. But we are able to use this to make our synthetic data. I'll show the results in a bit. But before showing the results, I want to talk about the most important thing of this conversation today, which is about the simulation qualification. And one thing that matters a lot when we have point clouds is the geometry. Unlike working with RGB cameras that we can look at pixels, do pixel comparison, and at the end of the day, we have 2 dimensions. Now we deal with 3D, which makes everything more complicated. One method that has been used a lot, and is pretty much new, is called histogram method. The reason that people like it a lot is because it is kind of easy to implement. The idea is that we take some samples of points from the real LiDAR scan and from the simulated one, and we convert the distance between these points into a histogram, and we can do some comparison metrics like Minkowski distance in the histogram. Of course, we can use a iterative closest point approach too, which is a point cloud registration method. If 2 point clouds are very different, we are not being able to overlap them correctly, and then it gives you the idea that, okay, these two looking very different. But as you can see, both of them are making everything flat in 1 dimension even. And the whole idea is that we are having 3D. So they are not able to give us information about the geometry of our work. Here again, I'm showing example for the point cloud simulation using the histogram. You see the blue and green one, they have different histogram sense. They have different peaks. They are both looking Gaussian, but having a very high tail. But this is, again, very difficult for us to say that, okay, if these 2 scans are really similar or not, or how bad our work is. Then, of course, we can use chamfer distance and more newly introduced density average chamfer distance. The density average chamfer distance is a very nice one because it has a higher and lower bound, saying that, okay, it's not going to get above the value of 1, which is very nice. However, for chamfer distance, there is no upper limit, so it's becoming more difficult to give you a very good way of comparing 2 LiDAR scans with each other. One of the issues, I don't call it issue, but one of the small things with density average chamfer distance is this alpha in the exponent of this exponential function. Normally, we decide what value to put there. If you look at the equation, P1 and P2 are the values of the points in real and the simulated ones. If they are completely the same, P1 minus P2 will be 0. But if they are different, then the alpha starts playing a role, and how big it is decides. It will give us the idea about how big of the exponent will be at this, in general. But at the end of the day, I would say that density average chamfer distance, especially because it has lower and upper bound, is a very nice metric, and it is geometric average. Here, I'm showing the result of our own simulations. Of course, you can see that they're similar, but they have some differences, especially in the vegetation part. In the plot, you see that we did both density average or we call it DCD, with alpha equals 1 and normal chamfer distance. And the x-axis shows as the time goes by or as we move through the path what you see. When the difference becomes larger, they are mostly because we get to the curves, and it shows that our simulations does worse when we get to the curves, and actually it does very bad when we have lots of vegetations. This is another example when you see a sharper curve. Actually, here the road wasn't paved, it had a very rough surface, and that caused some dissimilarity as well, meaning that our simulations are not necessarily very good when the ground is not very smooth. But overall, when we use chamfer distance, it's based on one complete scan. So it doesn't give us an idea of what's happening in each of these objects within each scan. For many of our works, we don't necessarily care about that vegetation. Like if these trees' leaves don't look too good, who cares? I want to make sure that the road is safe and the driver is safe, and for safety purposes, I'm not caring about if like this building looks good or not as well. So it's very important to be able to look at each object and do chamfer distance for that. That is not that easy, and it gets us to segmentation. So if we want to do the chamfer distance comparison for each of these objects, we need to do segmentation. Again, we can use deep learning models compared to RGB cameras. Using point clouds and trying to do segmentation is way more challenging. But there are some successes. That's normally the best segmentation models. They do about 70 to 75% accuracy, which is not bad, but it's not amazing. At the same time, when we want to use these models for our own simulation, keep in mind we do ray tracing, so we don't necessarily have intensity, but most of all these models are being trained based on intensity too, so it makes our segmentation even looks worse. But if you look at here, you see that the model, when we map the intensity from the real, from the ground truth, does an okay job. And it is becoming very difficult for the model to distinguish between the real and simulated scans. So from the other talk that we had earlier, the person was talking about using YOLO, and in some part, YOLO wasn't able to really distinguish if this is a real car or a simulated car. For point clouds, we are not there yet for two reasons. The first one is that the models themselves, like the trained models, machine learning models themselves, have has lower accuracy. So it's very difficult to trust a trained model that itself has high error in it. But in general, you see that the model has done very good job in vegetation. One of the things that we were thinking at first was like, we don't do very good in vegetation, but you see that it was able to, these gray ones are actually the vegetations, that it was able to segment it correctly and doesn't differ between the real scans and the simulated ones. But what we want to do is do a better clustering, and doing a better segmentation in a sense to be able to then use chamfer distance on those objects. In this case, we are using graphs. So graphs are very friendly, actually. They seem very scary, but they are actually very nice. How they work is like they are some points, and we try to connect them based on some logic. And they have matrix representation, And these matrix representation are very powerful mathematical tools helping us to be able to compare two graphs or 2-point clouds in our case in a way more quantitative way. Other thing that they are able to do is doing community detections. So these communities are meaning that they are points that are closer together and make a community. Here I'm showing you an example of our work. The blue one is the ground truth, and the red one is a simulation. We call it perturbed one. So it's not a real simulation. We took the ground truth, we perturbed it around just to show you how best case scenario they might look. And then we use graph-based community detection approach. This way, these C sum values are the communities that it has been made out of this graph community detection. And you see, like, for example, C15 is 1 tree. So one of the first things that we can get to compare the simulated versus real scans is to see if these communities match well. So if if the same graph with the same all parameters is able to find the same tree, for example. So to give you an example, in real data, when we do the simulation, the match of the communities is about 60 to 70%. Then we can go look at each object and see if the important objects have been flagged as the same community or not. Normally, for C7 and C17 are 2 cars. Normally, for cars, it does well. We have problem with vegetations again. The other thing is that if we are closer to the source and we have more point clouds from the beginning, for the synthetic measurements, it does a better job. But in general, it's a powerful way of segmentation, and then for each segment, we are able to look at how good this community is matching between real and simulated graphs. So if I want to give you a summary on the graph community detection and how we can go forward with this, it is a way to determine the similarity between each community that we built. We decide which communities are more important for us. So for many works, we care more about cars or pedestrians, and we can focus on them and see how well they are matching rather than just looking at the whole the whole scan and decide. We can conduct chamfer distance in each community and do the analysis of how good they are, and we can utilize dynamic graph analysis. The other power of graphs are they are temporal. We can have graphs that they are changing in time, and then we can see the change in point clouds from one scan to the other scan. So that being said, I'm going to pause here, and if you guys have any questions, I'm more than happy to answer.
Thank you, Ghazal. Questions, please. Thank you.
Hi, this is Nishant from Deloitte. Couple of things. So one thing, you talked about chamfer distance here, but we are talking about the point distance. So it is giving you the distance, but not the geometry, right? So how do you then realize the terrain? Because you are still getting a 2D cloud, but not the terrain. So is it a flat or is it uphill? You don't know. So maybe this is one. Second was the typical value of alpha from your experiences, and the third one, or
yeah, that's still chamfer distance has some symmetry, so it is more geometry ever, but you're completely correct that at the end of the day, even chamfer distance is not completely geometric approach. And, like Earth mover distance has the same problem. All of them are having this idea that you have to map to 2D. They are more geometric approaches like homology or persistent homology, but they become very complex and computationally expensive. At least chamfer distance has this kind of understanding of symmetry, so it gives us a better understanding of what's happening in 3D. But that's about it. You're correct.
And any clue about alpha? What's the typical value for alpha?
So in our work, we tried, actually there's a paper is coming if you check our group. We did try different values very close to 0 to 1,000, and something between 1 to 10, it's the best value for our work. It's more trustworthy.
And another one, so you talked about the geography and the cloud, but are you also considering other factors, for example, the terrain or the simulation, but in an icy condition or in a windy condition? This is another dimension to the same simulation environment. Are you also considering that?
Yeah, we haven't done anything on terrains. Like terrains doesn't make more problem from our perspective, but you said ice. For that, we haven't done anything.
Because if you are creating a complete simulation environment, that for the OEMs it is important to know the same terrain in a windy condition, how my vehicle will be.
Yes, definitely. It is something that we are going to go that direction, like the whole weather condition differences, especially that we are in Canada. But at the moment, we are just doing the very clean condition data.
Other questions? No? Well, I have one question, Ghazal. Have you looked at other sensors apart from LiDAR? Like, for example, cameras, ultrasonics, radar?
So yes and no. We have touched upon different sensors, but LiDARs are the ones that we are more advanced at the moment. Definitely we are looking to go forward for radars as well, but not necessarily RGB cameras because there are lots of companies already working on them.
Other questions for anybody? No? In that case, I'd like you to thank Ghazal for her excellent presentation. Thank you.